Hey everybody! In this video, we are going to go over two FRQs on the topic of equilibrium, and these come from the AP exam. So here we have a reaction and its K value. Number 1, the polyatomic ion is commonly abbreviated as EDTA4-. The ion can form complexes with metal ions in aqueous solutions. A complex of the two ions form according to the reaction above. So this is the reaction, and they're all in a 1:1:1 ratio, which is nice. A 50 ml volume of a solution that has an EDTA4- concentration of 0.3 molar is mixed with 50 mL of 0.2 molar of barium nitrate to produce 100 milliliters of solution. So let's read what A says. Considering the value of K for the reaction, determine the concentration of Ba-EDTA2- complex ion in the 100 ml of solution. Justify your answer. So for this problem, I'm going to zoom out a bit, and let's write an answer to this. So considering the K for the reaction, we see that the K is gigantic. It's 7.7 times 10 to the 7. And since this is such a large K, we can assume that this reaction essentially goes to completion, because if you remember from a video about Ka and Kb, if the K is greater than about maybe 10 or 100, it usually means that the reaction goes to completion. So in this question, we can say that for A, we can assume the reaction essentially goes to completion since K is very large. Therefore, we can treat the question like a limiting reactant problem where one or the other product will be consumed completely. So to do limiting reactant problems, we have to find the number of moles of each of the reactants and see how much of product they can produce. So let's try to find, well, I would first try to find the moles of Ba2+. Now this is going to involve volume and concentration, obviously. So we know that there are 50 mL of the barium nitrate, so let's start off by writing that. 0.0500 liters of barium nitrate. And we know that the concentration is 0.20 molar, or 0.20 moles of the barium nitrate per liter. So we need to find the moles of barium 2+ though, and we know that for every 1 mole of barium nitrate, we have 1 mole of barium 2+, since right here there's only 1 barium for every 1 formula unit of the salt. So doing the math, we can cancel out the liters and the moles of barium nitrate to get ourselves the number of moles of barium 2+. So 0.05 times 0.2 is going to be 0.01 moles. Well, let's add the extra 0 for sig figs, moles of barium 2+. And this can produce a maximum of exactly 0.010 moles of the complex. Okay, let's try to find the number of moles of the other compound, which would be the EDTA4-. Now this is the same idea. We take the volume, which is this, so EDTA4- times the molarity, which is, let's see, 0.30 moles of the EDTA4- ion per liter, and we can simply multiply those out to get the moles of EDTA. 0.05 times 0.3 is 0.015 moles of EDTA4 minus. And since the reaction is 1-to-1, we know that we can produce a maximum of 0.015 moles of the complex. Now, which ones are the limiting reactant? Well, it's the one that can produce less stuff. It's going to be barium. Ba2 plus is limiting. So we base our products off of it. Okay, so let's now find the moles of the complex. So we know that a total of 0.010 moles of the complex, which can be written as BaEDTA2 minus, will be produced because barium is our limiting reactant, and this is divided by the volume of the solution, which at the end was 0.1000 liters. And 0.01 divided by 0.1 is going to be 0.10 molar of the BaEDTA2 minus complex. Now that's the answer for A. Let's take a look at B. So what does B say? The solution is diluted with distilled water to a total volume of 1 liter. After equilibrium has been re-established, is the number of moles of barium present in the solution greater than, less than, or equal to the number of moles of barium present in the original solution before it was diluted? So what basically happened was that there was, 0.1 liters originally, and this was at equilibrium. But afterwards, a person decided to dump a bunch of water to make the solution 1 liter, and now the system's not at equilibrium because each of these three got diluted, and that can impact equilibrium somehow. But after some time t, the system returns to equilibrium. So they're saying, is the amount of barium-2 plus here greater than, less than, or equal to the amount of barium-2 plus here? Well, we can figure this out by doing some equilibrium expressions, because if this system is dealing with equilibrium, we should attack it with some equilibrium expressions. So for B, we are going to take a look at the equilibrium expression for this reaction. So we know that K is going to be equal to the concentration of the complex ion. So it's going to be that, and that's 2 minus, over the concentration of the ions that make up the complex ion. And voila. So let's assume that these concentrations are the ones at equilibrium before. So, for example, these three will be the equilibrium concentrations before. But someone decides to add some water to it. So guess what? The system will not be at equilibrium anymore. So we have to write a Q for this instead of a K. So what happens to the concentrations when the volume is diluted from 0.1 liters to 1 liter? Well, we can use a simple equation called M1V1 equals M2V2. This is the original, and this is the concentration after dilution. So before, M1 times 0.1 liters is equal to the final concentration times, let's see, V2, which was 1 liter. And we can divide both sides by 0.1 to get that M1. Well, let's see. So if I divide both sides by 0.1, we would get M1 equals 10 times M2, but we want the concentration of M2 alone. So, therefore, M1 over 10 is equal to M2. So to get the new concentration after dilution, all we have to do is take the old concentration and divide by 10. So what we learned from this is that by diluting the volume from 0.1 to 1 liter, we essentially multiplied our concentrations originally by 1/10. So let's write the Q expression based on this. So each of these concentrations will be multiplied by 1/10 after the dilution, because these are the new conditions. So this is the new condition. All right, so the new conditions involve, well, it wants 1/10 of the original concentration of the ions. So let me try to write this in a proper notation that will make a lot more sense. So let's not put brackets there, and let's instead just put 1/10 times the concentration of the Ba EDTA 2 minus, and this is all taken to the first power because, the coefficient is 1. And same thing happens to the barium 2 plus, and it's taken to the first power once again. And let's do that one last time for the EDTA to 4 minus, because by diluting the solution, we essentially multiplied all our concentrations by 1/10. So we can simplify this and pull out the 1/10 and 1/10 to make, 1 over 100. Now dividing by 1 over 100 is the same thing as multiplying by 100. So therefore Q will equal to 10 times, well, what we started off before. So BaEDTA 2 minus over the concentration of barium 2 plus times the concentration of EDTA 4 minus. Now, what do you notice about this Q? And what do you notice about the K before? Well, the Q seems to be 10 times the K, because K is this, and if K is this, and we're multiplying it by 10, that means that Q is equal to 10 times K. So our original condition was K, but by diluting it, our new conditions are 10K. So let me ask you something. Is Q greater than, less than, or equal to K? Well, our Q is unknown compared to K, but we know that Q is 10K, and 10K is greater than K, because K is always a positive value, and 10 times a positive value will always be greater. So, therefore, Q is greater than K. Now, if Q is greater than K, we have too many products, which means that the reaction will go backwards. So let me write all that. And because of this, the moles of Ba2 plus, which is a reactant, will increase for the system to re-establish equilibrium. So I think I am writing toward the pause sign, and I'm just going to put a dot there. But if I were you, I would write the full letter, but I can't because I ran out of space. So the answer to this question is essentially the concentration of Ba2 plus will be greater after the dilution. So therefore, for B, well, let's write it down on the side so that's close by. We can say that, therefore, the moles of Ba2 plus is greater than originally. Okay, so that's the answer for B. And yeah, let's go on to number 2. Hopefully number 2 is less challenging. So let's zoom in so that you can see it. So number 2, when heated calcium, well, let me fix the layer first, sorry for that. So when heated calcium carbonate decomposes according to the equation above, let's see, so this decomposes into a salt and some CO2 gas. In a study of the decomposition of calcium carbonate, a student added 50.0 grams of powdered calcium carbonate to a 1.00 liter rigid container. The student sealed the container, pumped out all the gas, and heated the container in an oven at 1100 Kelvin. As the container was heated, the total pressure of the CO2 gas in the container was measured over time. The data is plotted below. So as you can see, the reaction is going up and up, so that means that the pressure of the CO2 gas is increasing and increasing, and then it flatlines, probably because it reached equilibrium, right? So let's go down here and read what they want. The student repeated the experiment, but this time the student used more, or 100 grams, of the powdered calcium carbonate. In this experiment, the final pressure in the container was 1.04 atmospheres, which was the same as before. Ooh. So even though they used more of the calcium carbonate, you still produce the same amount of gas at the end, or the same pressure to be precise, and this probably has to do with equilibrium. So let's figure out what's going on. A. Calculate the number of moles of CO2 gas present in the container after 20 minutes of heating. So we need the moles of CO2, we have the partial pressure of CO2, we have the temperature, 1100, and we have the volume. Hey, guess what? PV equals nRT seems like the perfect fit for this problem. So let's get going. PV equals nRT. Our pressure is 1.04 atmospheres, and our volume is 1.00 liters, and this is equal to the moles times 0.0821 times the temperature, which is 1100 Kelvin. And doing the math, 1.04 times 1 divided by 0.0821 divided by 1100 gives us that our N, or the number of moles of carbon dioxide gas, turns out to be around 0.0, let's see, how many sig figs do I want? I'll say 3 sig figs. Actually 2 sig figs, since there's no, dot after that. Since there's no dot after that, this has 2 sig figs, and therefore our answer should have 2 sig figs. So I'll write that. So 0.012 moles of CO2 gas. There you go. That's A. B. The student claimed that the final pressure in the container in each experiment became constant because all of the calcium carbonate had decomposed. Based on the data, do you agree with this claim? No. And you might be wondering, why did I say no? Well, even though the student added more calcium carbonate than before, the amount of gas, or the moles of CO2, stayed the same, since the pressure of CO2 stayed the same. And this would not happen if the CaCO3 all decomposed, because if more stuff decomposes, shouldn't the pressure increase? But it didn't, so obviously not all of it reacted. So we can say something like this. Increasing the amount of calcium carbonate did not change the partial pressure of CO2, or the amount of CO2 at equilibrium. So let me actually write the entire thing, equilibrium. Because of this, so let me write that C. Because of this, this means that the extra CaCO3 added did not react at all, or else the partial pressure of CO2 would be much larger. Therefore, not all of the calcium carbonate reacted in the 100-gram sample. So that's the answer for B. And let's take a look at C. After 20 minutes, some carbon dioxide was injected into the container, initially raising the pressure to 1.5 atmospheres. Would the final pressure inside the container be less than, greater than, or equal to 1.04 atmospheres after reaching equilibrium, since final is assuming, after it reaches equilibrium? So, explain your reasoning. So, let's figure out what's going on here. So, it says that they add a bunch of CO2, and what will happen after some time if you leave it in the container for some time? So, let's see. Let's write the Kp for this reaction. The Kp for this reaction is going to just be the partial pressure of CO2. And it seems like at equilibrium, the partial pressure of CO2 is 1.04 atmospheres. Therefore, since the partial pressure of CO2 is 1.04, this means that the Kp must be 1.04. So any K greater than 1.04 will cause the reaction to go backwards to reduce the pressure. So I would say that the final pressure would be equal to 1.04 atmospheres because, let me scroll down a bit, upon increasing the partial pressure of CO2 to 1.5 atmospheres, the Q of the reaction is 1.5. Since 1.5 is greater than 1.04, and since Q is greater than K, the reaction will go backwards and reduce the pressure of CO2 until it reaches 1.04 atmospheres, which would allow the system to return to equilibrium. So I think that would be a sufficient answer for C, and now let's take a look at D. Is there sufficient data obtained in the experiments to determine the value of the Kp for the decomposition of calcium carbonate at 1100 Kelvin? Well, funny thing is that I just did that. So yes, K only relies on the partial pressure of CO2. Therefore, Kp is equal to the partial pressure of CO2, which at equilibrium is 1.04 atmospheres. So that would be the answer for 1D, and it was pretty fast. And look at that, we're done with number 2. Now let's take a look at the answer keys to see if you want to look over things. So for 1A, 0.1 molar was the correct number, and we did a great job doing that. And look at B. I used this explanation right here to explain the fact that more Ba2 plus will be formed than, in the original solution. And this is based on that simple fact. So read that over if you're kind of confused, and let's move on to question 2. So A was not that bad, but it seems like they kept 3 sig figs instead of 2. And, I guess that's fine. I guess they said that was 4 sig figs, but technically it isn't since there's no, dot over there, but whatever. I'm sure it will be fine either way, but I guess, I don't know. Let's just move on. For B, they state that you should not agree with the claim, and I used explanation 2 to explain that. So the 2 different experiments reached the same constant final pressure. Since increasing the amount of reactants did not produce more products, there's no way that all of the CaCO3 reacted. Instead, an equilibrium condition had been achieved, and there must be some solid in the container. Cool. So let's see. So you disagree with it, and you have to talk about justification using stoichiometry, and we kind of did that. So let's move on. C. So it says that it would be equal to 1.04 because the equilibrium pressure is 1.04. And, if the reaction has too much products, it'll shift toward the reactants. So this is Le Chatelier's principle. And the amount of CO2 will decrease until it returns to the equilibrium pressure. Now for D, we said yes, and boom. So that's all for this video. I hope you all learned a lot, and have a nice day, everybody.